Alright, let's finish up this lecture. Next, visual binaries. So this is the ideal case. A visual binary is a system where you can actually see the two stars, different stars, either through a telescope or with the naked eye. One example of a visual binary is Sirius. We have Sirius A and Sirius B. Sirius A is the larger star, Sirius B is the smaller star. And with the telescope you can actually see that there are two different stars. This bright star, Sirius A right here, has a faint companion, the small one, Sirius B, which is a white dwarf. So both stars can be seen directly. Now, over the years, astronomers can watch these two move and map their orbits. So this purple line is going to map the orbit of Sirius A, and this white line maps the orbit of Sirius B. By the time we get from 1960 to 1970, we've determined the center of mass, and by the time we get to 1990, we know the orbit of this object right here, these two stars. Okay, now spectroscopic binaries. These are usually binaries with separation A that cannot be measured directly because the stars are too close to each other, so they appear to be as one star. There's a limit on the separation, and thus the masses can be inferred in the most common case, spectroscopic binaries. Write that one down. You already wrote down visual binaries, hopefully. So spectroscopic binaries, we look at this spectroscopic view here. The approaching star right here, remember our Doppler shift, it's blue shifted. The receding star is the star going around in this direction, so it's red shifted. So you see these two spectral lines producing the red shifted and the blue shifted lines. The Doppler shift measurement then shows that those two Doppler lines start to get closer together as they go around in their orbit. Here, when we see them kind of in the same field of line, right here, this same line, then we get A and B lines lined up. Now they're going away from each other, and these lines are going away from each other, and at their farthest point they're back to here. So the Doppler shift, remember we can measure radial velocity with Doppler shift, or if the star is going away from us, we can measure how fast it is going away from us. And from that information you can estimate a separation between the two. And if you've got an estimate of the separation, you can estimate the mass. Here's an actual example of spectroscopic binaries. Mizar is a spectroscopic binary star. And this is what two spectroscopic views of that would look like. Computers these days use the dip in the graph, so the dip in the brightness as they come together. Or not that, that's the emission line, I'm sorry. These are the emission lines. So you can see it's the same as what we looked at back here with these spectroscopic lines. It's just a different way to show that. Here they're lined up, here they're going further away, here they're at their furthest point. And they get closer, they line up, they go away, they get closer, and then eventually line up again. Alright, now this is an interesting one. These are called eclipsing binaries. Usually the inclination angle of a binary system is unknown. We don't know. So it's hard to, there's a certain bit of uncertainty because of this distance, because it's tipped 45 degrees. This distance is going to appear a little bit different to us. With eclipsing binaries, we know we are looking at those on an edge-on system. Like if we were to take a CD and look at it edge-on. And what happens is you get what's called a double dip in the light curve. As a small hot star orbits a large cool star, we see their total light. As the hot star crosses, we see the dip. As the hot star uncovers, the cool star goes back up. And when the hot star is eclipsed behind the cool star, you see a big dip. Okay, we call that the double dip. And no, it is not George Costanza double dipping his chip. Seinfeld. It is the dip of the light there. We call that the double dip light curve. Okay, another example, Algol in the constellation Perseus is an eclipsing binary. They don't totally eclipse each other, so we see this little dip right here when they're edge on. But here would be the dip as one goes behind the other. We can infer that this system contains two stars of very different surface temperature orbiting on a slightly inclined plane, and we know that because of this little dip right here. So this is what Algol actually looks like. This is the little dip. As the hotter, brighter star passes in front of the cooler star, and when the cooler star passes in front of the hotter star, we get the big dip, double dip. Now remember, the higher a star's mass, the more luminous or brighter it is. Therefore, we can use the HR diagram to put down masses of stars. High mass stars have much shorter lives than low mass stars, so these blue giants, they burn out really quickly. If you look at this star compared to our sun, compared to this star, our sun is going to have a lifetime of about 10 billion years. This is only 30 million years. Now that seems like a lot, but with the star, this is actually not a lot. That's very fast, 30 million years. Over here, check it out, 3 trillion years. That's a huge amount of time. So very low mass stars burn their fuel very slowly and last a lot longer than these high mass stars. Let's see, here in 1843, we noticed this eruption, or this very dramatic mass loss created these double lobes on this system right here. Okay, now this relates to what's called the maximum mass of main sequence stars. So main sequence stars, their maximum ranges somewhere between 50 and 100 solar masses. More than that, and the more massive clouds, they just fragment into bigger, or smaller pieces rather, during star formation. And these very massive stars lose a lot of their mass with solar winds. And in this case, this binary system had a 60 solar mass star and a 70 solar mass star. And because we get larger than this number right here, there was a dramatic loss of mass as this exploded. The minimum mass of a main sequence star is about 0.08 or 8/100ths the mass of the Sun. The reason why anything less than this mass does not become a star is because it just is too small and it doesn't get hot enough with the pull of gravity to ignite in thermonuclear fusion like we talked about. So anything smaller than that is called a brown dwarf. Here, right here, this illustrates the ideal situation to determine properties of stars. Stars that are in this 62 parsec radius right here from the Earth, we can determine properties of all stars within this volume. The problem that we have with saying, okay, so many stars, this X number of stars are blue supergiants, and X number are red giants, and X number are main sequence, and X number are red dwarfs, is we are slightly biased towards those brighter stars. Brighter stars are a lot easier to observe, and so we are slightly biased towards those brighter stars, and that's important to remember as we do a survey of stars. Now this graph shows, it's kind of a HR diagram. Notice the main sequence, white dwarfs, supergiants, and giants, imposed on a 3D gram. We add another axis, and these are the density, right? Stars per 10 to the 6 parsecs cubed area. So by far, red dwarfs are the most common stars. Why is it we don't see a lot of red dwarfs? Well, red dwarfs are really faint and hard to see. But we know that they are the most common kinds of stars. Bright, hot, blue main sequence stars are rare. Smaller ones are more common. So our sun is a little bit more common than these blue ones, but not quite as common as red dwarfs. Okay, white dwarfs are high, but if you look over here, supergiants and giants don't even make a blip on this. They are so uncommon. Very, very rare stars. Very, very bright, so we may be skewed a little bit to noticing these, and you might think, well, I can see them all over in the sky. Yes, but if you somehow had a way of detecting red dwarfs would literally just dot the skies all over the place. And that is it for this lecture. I hope that was informational, and I hope you took good notes. I will put the links of these videos on YouTube if you need to go back and see anything. Please email me if you have any questions. Now I would like you to do the STARS web quest that Mr. Wayman is going to pass out to you. Use the tablets. Please put the tablets back properly. There's a link on Moodle. If you go to Moodle and click on the resources tab, it will have the links to go and do this web quest. If you don't finish this web quest today in class, please finish it at home. It is a notebook assignment, so it stays in your notebook. Alright, good luck, and I will see you next week.